Okay, so now we will be looking at threaded binary trees. So the idea with threaded binary trees is we just add additional links or thread to our link representation. In particular, we will try to fill up the null pointers that we have in our link representation for our binary tree. So we know that given our representation, we can deduce actually that there, given n node, there will be n plus one null link. So, well, instead of having them as null or instead of having useless links here, what we can do actually is we can add threads to our binary tree. So the lines here with arrows, the black lines here are what we call the tree link. So basically, these are these links, the pointers that point to an actual node in the binary tree. However, we can actually add threads. So the broken lines here are called threads, and where will they point to? So the idea is instead of having them as null pointers here, they will point to something. Okay, and where will they point to? So well, one possible way is to make them point to the in-order successor or the in-order predecessor of a particular node. So what is the in-order predecessor or the in-order successor? The in-order predecessor is basically the node that comes before the node when we reverse the tree in order. While the in-order successor is the node that comes after the node when we reverse the tree in order. So for example, for node U, the in-order predecessor is U because that is the node that comes before node U in pre-order, in order, sorry. And node I is the in-order successor because that node, if we write this in order success, in order reversal, node I is the node that comes after node U. So instead of having null node here, we point it to the in-order predecessor and the in-order successor. And why would we want that to do? Well, we will see later that it will make our lives uh, easier when if we want to do in-order reversal. Basically, you now know what is the in-order successor or the in-order predecessor of a node. So, but I think one question that we want to ask. So, we know that, for example, when we call L son of U, how will we know if the left hand is actually an actual left hand of U, or if it actually points to the in order predecessor, or if we call the right hand of C, how do we know that the right hand pointer points to the actual node and not to another node or to the in order successor of C? So the general idea is if a node has no left hand or no right hand, then the left hand pointer will point to the in order predecessor or the in order successor. To do that, and answer the question we had earlier, we will be adding two more values to our binary tree node. So before we know that we have a left hand pointer and a right hand pointer, now we will be adding a left tag and a right tag. So the idea with the left tag and the right tag is if the left hand points to an actual node to its actual left hand, then the left tag will be one. However, if the left hand if the node has no left hand tree, therefore the left hand should point to the in order predecessor, then the left tag will be zero. So this will tell us, so the left tag will tell us whether the left hand pointer points to an actual left hand or if it points to the in order predecessor. The same thing with the right tag. If the right tag is 1, then that means the right hand pointer points to an actual right hand. However, if the R tag is 0, then it means that the right hand points to the in order successor. So this will be the structure of our node. So since the left hand of I is actually 2, the value of left and tag is 1. However, since I has no right hand and the right hand points to the in order successor, then the value of R tag is 0. And that is true for the whole binary tree. So we have a head node here. So why? Because we want to have a node where the left hand of the leftmost node and the right hand of the rightmost node can point to somewhere. So how do we know the in-order successor of a binary tree? Because we want to implement it. Because we want to know where we can find it. Here are two scenarios. If the node alpha has a right sub-tree, then the in-order successor is the leftmost node of the right sub-tree, this one. So if node alpha has a right sub-tree, then the leftmost node here, so we will just look at left tag, which node will have a 0 left tag at the left part. The leftmost node, so we will look at that, and then that node will be the in-order successor of node alpha. However, this is quite tricky. If alpha has no right sub-tree, so alpha has no right sub-tree here, then the in-order successor is the root of the left sub-tree of whose rightmost node is alpha. So we look at this definition in reverse. So this is alpha. This is the tree where alpha is the rightmost node and as that it is a left sub-tree. Because this tree technically, if we can draw a tree here, this alpha is also the rightmost node here, but here alpha, that this tree is not a right sub-tree. So the first tree such that it will be a left sub-tree is this tree, and alpha is the rightmost node, and the root of that tree, where this is a left sub-tree, shall be the in-order successor. So if you will be looking here, essentially, U is the rightmost node of this tree, which is the left sub-tree, and this is the root. So this is the in-order successor of U. So that's the idea there. For the in-order predecessor, we just reverse our definition. So if node alpha has a left sub-tree, then the in-order predecessor is the rightmost node of the left sub-tree. So if this is alpha, and it has a left sub-tree, then the in-order predecessor is the rightmost node. But if you will look, this definition A actually corresponds to definition B here. And definition B here, if alpha has no left sub-tree, then the in-order predecessor of alpha is the root of the right sub-tree. So this is the right sub-tree, and this is the root, where the leftmost node is alpha. Okay? And this definition actually corresponds to the first definition, the first property that we had here. So that is how we look for in-order predecessors and in-order successors. So I think one thing that you should look at is how do we implement that in actual algorithms. And another thing that you want to look at is how can we generate the same definitions for pre-order and post-order successor or predecessor. We have here one property. So if we have the sequence of left tag and R tag of a tree, and they are written in pre-order, then we can actually construct that tree. Okay? So, for example, we know that this is the pre-order sequence of the left tag and the right tag values of the tree. So how can we construct the corresponding tree? So we start with 1, 1. So that means that the root, because this is in pre-order, has both a left hand and a right hand. And then since we are in pre-order, we know that the next node is the left sub-tree of this node, and it's 1, 0. So we know that this node will have a left hand, but it has no right hand. And then, since this is the next available position, this is for 0, 0, this is the node, and there's no left hand or right hand. So for the next node, for 1, 1, since this is the only available position left, we can put the node here. If we know that it has a left hand and a right hand, the left hand has 0, 0, and the right hand has 0, 0. So given the left tag and the R tag sequences of a tree, and if they are written in pre-order, we should be able to construct the original tree. Okay? As reading assignment, I want you to look at our class website, and I uploaded there uh, a book section on reversal by link inversion and cyclotic reversal. So I will be leaving those things as part of your reading assignment.